In this video, we're going to simulate a NACA 2412 airfoil in Ansys Fluent, and we're going to include some verification as well. To get to this point, you can take a look at video from Cillian Thomas or Anthony T. And if you're in my class, you'll see videos that I've produced for this as well, essentially copying and following what they've outlined. So, for this video, we're going to review some metrics for airfoils and experimental data. We're going to then do a simulation for our airfoil at an angle of attack at 0 degrees and Reynolds numbers of 2.2 million. We'll get into some of these other details as well concerning transformations for simulating angles of attack, and then being able to run an additional simulation at an angle of attack of 4 degrees, and setting up table design points for angles of attack ranging from -8 to 18 degrees. So some of this builds off of what Cillian has done in this very nice video, and expands a little bit to look at how you can create this table design points pretty easily and use appropriate transformations to figure out the coefficients of lift and drag. So moving forward, what we have for an airfoil, if you're not familiar at this point, you probably well, anyway, this may be boring for you. But we have an angle of attack now, which we're thinking about varying relative to our free stream velocity. Okay, and something to keep in mind is that the lift and the drag forces, not drawn super well here, or not modified super well, it's mine, of course, is that the drag force is going to be parallel to the free stream velocity, and the lift is going to be orthogonal or perpendicular to that. Okay, so if we get ourselves into a situation where instead of varying the rotational angle of the airfoil, okay, and we're keeping it steady, but we're now changing the velocities angle, the free stream velocities angle coming into the airfoil, we need to be a little bit careful about how we handle the lift and the drag, and we'll go through that in a little bit. These are formulas that you'll find in textbooks such as White or on the internet for coefficient of drag and coefficient of lift. And just be careful that this AP, this area that we're using, is the span times the chord length. Okay. Now, Cillian shows nice data in their YouTube video from Abbott for a Reynolds number of 3.1 million. And these data are available on archive.org. Just to change things up a little bit, there are additional data which you can find on the internet. It's a NASA report from a group at Wichita State, so a number of years ago. And I think these data are great in terms of how you understand and make a plot. Okay, you see they had typewriter and some sticky notes, I guess, so they put on graph paper. And it works. It works pretty well. So these data are for a NACA 2412 airfoil, and they were changing the surface roughness essentially, and then also including that Abbott data, okay, which you can also find. And I thought, just to change it up a little bit, we used the 2.2 million, okay, Reynolds number on a clean surface, and WSU stands for Wichita State University, and that's where this report, that's the origin of this report. So if we come down here, and this plot is for the coefficient of lift, and we look at this plot, and we see here that we have -4, -2, and then 0. So the kind of the slightly darker line, at least I think it's slightly darker. Maybe it's just an illusion because it's farther away. I don't know. But this is the 0 degree line. And then if we look at the square, and we zoom in here, we'll see that, okay, this is 0.1, and this is 0.2, and this is 0.3 and 0.4. Okay, so we're somewhere, okay, if the square, it's like about 0.2, okay? That's what we'll say, okay? And so I said 0.2 for a coefficient of lift, and if we come over here, this graph is a little more complicated than maybe the graphs that you saw on Abbott, because now it's plotting the coefficient of drag versus the coefficient of lift. So we kind of need to say, all right, well, it's 0.2 at 0 degrees for the coefficient of lift. All right, that's what we said here. So then we find out where do we have 0.2 for the coefficient of lift? Again, we're using the squares. So that's going to be, this is 0.2 right here. So, and then these are in 0.01 increments. So that's 0.04, 0.03, 0.02, 0.01. So this point right here is maybe 0.007, okay? Because it's kind of almost halfway in between 0.005 and 0.01, okay? And so that's what we're going to call it here, the Reynolds number of 2.2 million. This velocity is going to be, the associated velocity is 33 meters per second, okay? And that's based on calculating the Reynolds number with, where do I have the numbers here? Maybe I don't have the numbers here, but the density is around 1.2 kilograms per meter cubed, and the viscosity is something like 1.8 times 10 to the minus 5 meters Pascal seconds. So let's go ahead and now that we've looked at a little bit of the metrics and we know what we're trying to simulate, let's go into Workbench before we continue. So we've got the geometry and the mesh set up. Thank you very much, Cillian Thomas, Anthony T. And we are going to now double click on the setup. And here we're going to use double precision, and we can use 4. And we'll hit start. And Fluent is loading up. We'll change these dimensions a little bit if it lets us, so you can see a little bit better. Okay, yeah, lots of clicking of that's okay. I guess someday I should probably click this don't show this message again. But I haven't done that. I'm nervous about changing the defaults. All right, so we're going to follow a procedure outlined by Cillian, and in fact, the procedure here is much more straightforward than creating the mesh or creating the geometry in an Ansys. So we're going to use the viscous, the default model, the viscous SST, and then we're going to use air, which is already in here, so we can leave that as it is. And if we had a different fluid that wasn't air, we would have to come in here and change the cell zone conditions. Things start to get interesting, though, when we look at the boundary conditions under inlet. So something pretty important to recall here is that the inlet that we've defined for our mesh is actually, or for our domain, it's actually this entire top surface and then around and then down and bottom for our C-shaped configuration. So if we just use our velocity as normal to the boundary, right, we're gonna have air coming in at kind of very different angles because it'll be normal to the boundary. So we don't want to do that. We want to make sure that we have it in terms of either magnitude and direction or components. Okay, we're going to be using components later, so let's go ahead and use components here. So I'm going to say it's going to be 33 meters per second in the X direction. Apply, close. And I'm pretty sure that's what Cillian did too, Cillian Thomas. So then we can come down here to the reference values, and we're going to use MATLAB and calculate coefficients of lift and drag a little bit later based on force and drag force instead of coefficients of drag and coefficients of lift. But if we want to use the calculations that Ansys Fluent provides, we need to make sure that these reference values are correct. So here for velocity, let's just put in our 33 meters per second. Okay, the area, all right, remember that's the span times the chord length. And since it's a 2D simulation, essentially the span is 1 meter, and the chord length that we've been using is 1,000 millimeters or 1 meter. So that is set for us now. Under the report definitions, we can go ahead and add or make some new drag coefficient and drag force. So this will be the drag coefficient, and we're going to do it on the surface like that, and it's fine. We'll print it to the console as well. And whoops, oh, I double clicked that there. Okay, so now that's set. We'll go ahead and create a drag force as well. Okay. And click there. There we go. Print to console. Now, something to keep in mind here, you see the force vector is 1, 0. So it's going to be going to the right. And it'd be nice if Ansys allowed us to like put a different parameter or variable, but it only allows numbers. Like I can't put any letters, right? So that means that we will want to do a transformation later in order just to keep these force vectors constant instead of changing them. And I think that's a nice little trick that that I'll show you how to do in a little bit. Then we're going to do lift. I guess we can do lift coefficient. So we'll do this as lift coefficient. And again, we click on the wall surface body and we'll print a console. We'll have a lot of things coming out in the console. That's over here. And then we'll do another lift, but this time we're going to do force. Like that. Click there, also print to console, and hit OK. So these are what these values will be reported, and they're calculated on the surface of the airfoil. And you're like, where is that airfoil? Well, it's in there. It really is. Okay, right there it is. All right. For monitors, we can look at the residuals for convergence. 0.001 is probably a little bit low. I think Cillian Thomas uses, well, he does use 1 e to the minus 6. I'm going to use 1 e to the minus 5. I think that people would agree that for this particular simulation, these results are going to be just fine, and we can maybe speed up the amount of time or reduce the amount of time we have to wait. Okay, so we hit OK there. That's in. For the initialization, there's not much to really do. You can hit initialize here, or you can right click here and do initialize and calculate. Either way, sometimes it's just kind of nice to have it set up so that you know whether or not after the 10 iterations for hybrid, okay, that it's fine. It's okay. Sometimes it gives you a warning, and a lot of times you can ignore it, unless it doesn't, unless it gives you an error. And then for the run and calculate, run calculations, we definitely need to put in some iterations. We can put in 1,000. That will be more than enough for the conditions that we're going to be running, the range of angles of attack that we've selected, and now for 0 angle of attack. So we're ready to go. we can go ahead and hit calculate, and we'll let it do its thing. And it's, you know, kind of, I think it's often soothing to monitor these, especially when it's rewarding, right? When things are converging, when the residuals are going down and things are not bouncing around. For certain angles of attack, I played with this a little bit. Let's say, you know, like minus 18 degrees. That did not converge, or didn't look like it was going to converge. I let it run for a while. It was just kind of bouncing around. Okay, but this one is, wow, it converged. That's very nice, and that's, you know, much thanks to Anthony T and Cillian Thomas for allowing us to be able to have a great mesh. Okay, now one thing we can do, okay, is look at the console and see what values it came out with for us. Okay, and so here are lift force and lift coefficient. The lift coefficient, all right, this was not the final value of 0.2107, but then went to 0.211121. It's right, you see, but essentially it finished at 0.0 or 0.21. All right, and if you recall from our calculations here, we were estimating from these experimental data that it would be 0.2. So this is a very nice initial result. Okay, and the coefficient of drag is going to be more off. I think that's what Cillian had, even at that slightly different Reynolds number that they were running. They were a little bit off. Let's see, there we are. If we come around, so it kind of wrapped around, the coefficient of drag is this one, 0.0097. Okay, and so that's 0.0097 and versus 0.007. That's you know, higher percentage difference, but nonetheless, that's not bad. Okay, for a first pass. So we've now been able to run this simulation, and let's talk about how we can think of approaching multiple angles of attack. So the first thing here is to note that we don't want to remesh and rotate that airfoil, okay, relative to the boundaries that we've set up. It's much easier to change the direction of the air flowing in or across this airfoil. Okay, so we can see, if we go and create a contour plot here, that, whoops, and let's see if it just does it. Yeah, okay, so we zoom in. You can see this was zero angle of attack, and we have a stagnation point at the leading edge, and then we have essentially a stream coming right off the tail, okay, the trailing edge, and it's essentially running, you know, parallel to the chord of this airfoil. Okay, but if we want to, instead of, say, you know, pitching the airfoil up at 4 degrees, instead we can bring the air in at 4 degrees. Okay, and so it will come up from the bottom and then hit this airfoil. Okay, and if we do that, we want to introduce a y component of velocity. Okay, and here are some ways to think about this. All right, so this is the case we have right now, where we have alpha equals 0, the angle of attack equals 0, and the free stream is coming in, and we have d parallel to the free stream, as it always should be. Okay, and it's also nicely aligned with the horizontal axis. Let's say that we have a very large angle of attack, 45 degrees, or even extreme angle of attack of 90 degrees, right? What we have to do is we have to bring the incoming velocity around. And this is not too complicated. We can think of our velocity vector, okay, coming in two components, an x component and a y component. And we can think, okay, for 0 degrees, right, it's just the free stream velocity, comma 0. At 45 degrees, it's going to be cosine for the x component velocity and sine for the y component of velocity, right? So if we want to run at 4 degrees, okay, let's just do a quick calculation where we have 33 times, that's the free stream velocity that we're using right now, cosine d of, so that's degrees of 4, okay, and that component doesn't change, so 32.92, all right, and we'll do 33 times sine d, 4 degrees, 2.3. So let's go back into Workbench and let that run a little bit, okay, while we talk about a couple other things for transformations. So we come up into our boundary condition, and here for the x velocity, we're going to use 32.92 and 2.3. Okay, 32.92. I can't remember things. I'm very tired. Okay, 32.92 and 2.3. Okay, where is it? 32.92 and 2.3. Okay, just make sure I got that. 32.92, good. Okay. And we hit apply, right? So now we're going to expect that things will change a little bit. And we'll let this run while we talk about what to do about lift and drag. Here, we want to reinitialize, or we want to initialize again, so we do initialize and calculate, and yes, that's okay. We're going to let it go. Okay. So if we change the angle of attack, okay, then we also need to change L and D. We need to rotate L and D appropriately, and these vector directions are pretty straightforward, okay. And sometimes, a lot of times, I rotate something by 90 degrees, and then I look at what the coordinates are, then I figure out what the sine and cosine might need to be, and what the sine in front of the sine or the sine in front of the cosine might be. Okay, so this is laid out. What is maybe a little less intuitive, okay, is let's say that Fluent is always giving us a drag component that's horizontal and always giving us a lift component that's vertical, okay? Oh, it's done. All right, so we can see in the result, okay, that for small 4 degrees, like we see here, right, that the stagnation point has maybe moved down a little bit, right? It says blue is when it's really close to 0. And we can see that the stream off the trailing edge, okay, has a little bit of angle to it. It's only 4 degrees, right? And we could keep doing these. That would be fun. All right. As we're discussing here, we got interrupted by Ansys spitting out an answer, which is always a pleasant interruption. Okay. We need to do essentially some type of transformation, or think about how this force relates, how both of these forces that Ansys is going to spit out at us, the red ones, how they relate, okay, to an lift force that's normal to the free stream velocity, and a drag force that is parallel to the free stream velocity. And it's kind of, this is like a statics problem, or a vector calculus problem, or like physics problem. We just got to think about L fluent and D fluent as a hypotenuse, okay? And it's a hypotenuse of two vectors added to each other, right? So I can go this way and then this way. And I put the right angle right here. And you see this, opposite side from alpha is what we would consider to be parallel to our desired drag force vector. And this one, which is adjacent to alpha, the way we've drawn it here, is going to be parallel to what we want as our lift force, okay? So this kind of like when you do the triangles for stress transformations, you can say, all right, well, this one, you don't even have to think, just think of resultant force on an object, very, very simply, right? It's going to have a component in this direction, right? This L fluent, right? Just like if I had two forces that are orthogonal to each other acting on a rock, right? What is the resultant force, right? That's essentially what we're doing here. So we have this force, L fluent, contributing, to this in this lift direction, and also the drag force. Okay, that drag fluent, right? D fluent right here is going to be also contributing to the lift. All right, and you see it's actually in the way this works with vector addition, it's actually taking away from that lift. Okay, because this is going to be going down. So you can write out that this component plus this component is going to be your desired lift force. So that's there. And then for the drag force, it's going to be the lift sine this component, all right, plus this component, all right, here, and that will give you the desired D. So we don't have to change the vector direction every time for the drag and lift reports. All right, that's nice, and otherwise it would be kind of tedious to change it every time. We can use this transformation in MATLAB afterward. All right, so and fortunately we can specify x component and y components for the incoming velocity with parameters and then the table of design points. Okay, so to do this, we're going to go back to Workbench and we're going to come into our inlet velocity and let's just put this back at 33 and this back at 0. Okay, and we click over here. We're going to do a new input parameter, and this other window is going to appear. We're going to call this the x velocity. All right, coming in. You could call it something else. You don't have to use that. I'm just going to refresh that, so I like that there. We're going to use it as an input parameter. Yes. Okay, and you hit OK. And it should update, and now it says x velocity. And here, we're going to create a new parameter. We're going to call this the y velocity. Okay, and right here, y velocity, and that's 0. I'm going to refresh that so it's in there. Scroll down, yes, it's going to be using it as an input parameter, and I hit OK. And then it updates here. I hit apply, I hit close. I don't know if you have to do this all the time, but I like to run it just before I start doing things with Workbench. Oh, but actually there's one other thing we should do before that. So for the reports, okay, I don't necessarily want design points for a drag coefficient because these are not going to be right. Well, I mean, they're right drag they're fine as long as L and D are horizontal and vertical, or L is vertical and D is horizontal. But I am going to take these lift force, the lift force and the drag force. These are essentially, if you go back to what we're talking about with the L fluent, all right, L fluent and the D fluent, all right, that's what we're spitting out, or we're going to spit out here. Okay, so we're going to go to lift force. I'm going to double click on this. and I'm going to now, I didn't create it as an output parameter, but now it will be an output parameter as well as printing out, and the drag force also will make it to be an output parameter, like so. Okay. This should then be set to go. We'll go ahead and run it. Oh, sorry, right click, initialize and calculate, okay. And it's going to go. Now, while this is running, I'll try to go over to MATLAB just for a second and explain what we've done here. What I've done is I've essentially created a little script that's going to give angles of attack, all right, which actually I'm not going to put these angles of attack into Ansys. I guess you could, because you have an opportunity to do like direction and magnitude, but we're doing X and Y components. And we have our V naught of 33. So I can create X velocity and Y velocity column vectors that I can paste in. Okay, so it ran. Things look fine. That's pretty close to, that looks pretty good. 0. Let's just make sure that the drag and the lift and the drag, yep, so lift was around 0.211, so that's good, and then drag, yep, we're back at 0.097. Okay, so this looks good. Let's close this. Yes, we want to quit. And we're going to take that array. So if I run this script, right, you see we're only thinking up to the X velocity and Y velocity up to this point, right? And it's just taking the cosine d of these different angles of attack. There are going to be 14 of them. And if I click over here on the X velocity, all right, it brings that up, and I can click, we'll click here on Y velocity, okay? These are what we're going to bring into our table design points. So now we go into Workbench, and we're going to double click on parameter set, and we're going to see here that yes, we have our DP0. I don't know if it's going to let me, but sometimes it does interesting things, but we do want to retain that one. But we want to, in the subsequent rows, paste in our values. So here's going to be the X component of velocity. So that will go right here, paste. Okay, and we got to paste in the Y component as well. All right, I suppose I could have put these in a matrix instead, so I didn't have to do this twice, but this is not bad, and yeah, it's good. So not at DP0, but DP1. And notice there is a repeat right here, 330, so it already says, hey, DP5 is going to be the same as DP0. That's fine. Okay, so this is ready to go. We can click Update All Design Points, okay, and it should start running. Now, this takes probably about an hour to run, and I'm going to show you the results, okay, that you should expect. So in MATLAB and in PowerPoint, actually, so here we go, all right. Here's what the table looks like, okay, and in MATLAB, what I did was I just copied and pasted these resulting lift force and drag force, okay, into, and you can copy them both. You can like select them both, and then it comes in as an essentially 2-column matrix, right, like here. And so these are the numbers that came in, and and then I calculated out the kind of this L fluent and the D fluent, right, that we had before, and then use that formula that we had, right, to create a set of what I'll consider to be the desired lift forces and drag forces. Then I could calculate my CL and CD off of these L and Ds, and then I could go about essentially plotting all of these things. Now, these lines right here, these are me just eyeballing. So they're not necessarily perfect, but I just eyeballed the experimental data that we were talking about earlier, and have angle of attacks for the CL experiment, the coefficient of lift experimental data, and angle of attacks for the coefficient of drag, because at least from what I could tell, they didn't have the same number, although I think maybe it's, I don't know what it is, maybe I'm just not reading it right, but these are estimates, okay? And then when you plot this, so I do a Control Enter, okay, it runs, and we will get a plot soon. Where is it? Okay, took it a couple seconds. All right, it looks something like this. So I was surprised actually how good the agreement is. All right, so you know, kind of modest angles of attack. It seems like we have very good agreement for coefficient of lift. All right, and the red pluses are from our experimental data, or not our experimental, but from the literature's experimental data, and the blue is from our simulations. Okay, and so we see that we're having difficulty capturing the stall. All right, it seems like our simulation is a little more forgiving, okay, than the experimental data, but you know, the onset of stall is, you know, it's within a couple degrees, so that's pretty good. We already discussed how we were kind of a little bit further off with our coefficients of drag, but I was pleasantly surprised to see that the trends are in a line, an alignment, even though when I was looking at the data, I was getting you know, negatives for drag forces, okay, but the lift forces, right, these are the L and D, just horizontal and vertical and horizontal, but when you do the math out, they come out to being positive still. So that was very exciting. Okay, so what have we done here? We've been able to simulate the NACA 2412. Okay, in Ansys Fluent, we used the importing the geometry as outlined by Cillian Thomas and Anthony T, along with their meshing parameters, which work quite nicely, allow us to be able to do these calculations pretty quickly. We have a table of design points for different angles of attack, and just, yeah, I was pleasantly surprised that the agreement was as good as it was. Okay, so, and then we set up a table of design points, okay, for angles of attack from -8 degrees to 18 degrees, and we've plotted it. The simulation is still running in the background, but if I ran this for about an hour, you'd see the results that I've already shown you. Okay, thank you for watching. I hope you found this information interesting and useful.